viewers, previously on our discussion we have tried to see about oscillatory motion and waves. At last we have tried to see some of the common terms that are we going to use for waves, like wavelengths. We have defined period, frequency, and at last we have tried to see about how to determine the velocity or the speed of a wave. Today we'll try to see the mathematical expression of waves. So mathematically it's possible to express waves. Previously we have used the mathematical expression of oscillatory motion. Like the displacement might be given using sine or cosine function as a sine omega t or a cos omega t for oscillatory body. It's also possible to have the velocity as the negative of omega a sine omega t or positive of omega a cos omega t for velocity. And for acceleration it's possible to have the negative of omega squared a sine omega t and the negative of omega squared a cos omega t. But here we are going to see about the mathematical expression of waves. Well, waves, for example, you can take a tensioned string, or you might take a level of water. Okay, you can take like this. Suppose here you do have tensioned string. If you exert a wave here, those particles at different points horizontally found at different points. For example, if I try to measure from this point, if this is my reference point, this is x equals to 0. At some point I do have at x equals to 1, 2, 3, 4 and different lengths at x something. There are different particles found here. As the wave propagates to the right, let's take a wave propagating to the right, is going to disturb those particles, and those particles are moving up and down, so that those particles are disturbed. And those particles are sometimes moving upward, and then as the wave is passing them, the particles are going to move downward. So that these particles are found at different vertical location. So the vertical location is represented using y. Okay, the vertical location is represented using y. And the vertical location of particles which are found horizontally at different position, x. Okay, the particle found at x, the particle found at one different position, you can take that, has different vertical location at different time t. Suppose here you have a particle which is x equals to 1. At this point, the particle might be found at y equals to 0, the vertical elevation. The vertical elevation is 0. But sometimes, at some other time, the vertical might be at the crest. Okay? At some other time, it might be found at the trough down there. So that this particle at different time t has different vertical function or vertical displacement. This is what it says. It's a pose, a displacement, and time variable, or temporal and spatial variable. And mathematically it's possible to express y, the vertical elevation, the maximum possible displacement, a sine kx, where k is known to be the wave number. We call it to be wave number, or it's related like k is equals to 2 pi over lambda, propagation constant. We call it to be propagation constant or wave constant and so on. We call it to be k. So that's as the wave tending to the right might propagate to the right or to the left. In this case we are going to see a wave which are propagating to the right. So y is equals to a sine kx minus omega t is a good expression of our wave which is tending to propagate to the right. If there is a wave tending to the left, it's possible to use plus sign. Okay, you can use plus, you can use minus, and so on. And for this case, and usually in your textbooks, it says that we are referring a wave tending to the right side. So the general expression of our wave can be given as a sine kx minus omega t. If there is a phase shift, it's possible to use phi. In this case, k is known to be propagation constant, and it's given to be 2 pi over lambda, and it's very helpful to determine the wavelengths of a wave. Whereas omega is known to be angular frequency, it's possible to have 2 pi times frequency f. Okay, 2 pi f, so that it's very helpful to determine the frequency of the waves. If you find the lambda of the wavelengths and the frequency of the wave, it's possible to determine the speed of the wave. Previously, we have said that speed of a wave is generally given as lambda times frequency f. The speed of any type of wave, mechanical wave, electromagnetic wave, is generally given to be lambda times frequency f. But there are other expressions or methods to determine the velocity or the speed of different types of waves. but the general expression is like this. So you can determine the speed of a wave as lambda times frequency, and you can determine lambda from the wave number or propagation constant, and you can determine frequency from the angular frequency w, so that it's possible to determine the speed of a given wave. And the speed of waves for different types of waves, in this case it's possible to have tensioned string. The speed of a wave in a tensioned string, if you have a tensioned string and plug and produce a wave here, so that the speed of a wave depends on the tension T, and there is a variable, it says mu, which is a linear, measures the linear distribution, and mu is given to be mass per length. The mass of the string divided by the length is known to be the measure of mass distribution. Therefore, it's possible to find the velocity v of the wave in tension string as the square root of tension T over mu. You can find like this. Now let's try to solve one example. Here it says, suppose a wave is given or expressed using this function. It says that the vertical displacement y is related like this: 4 centimeter sine 0.5 pi x minus 10 pi t plus pi over 6. It's expressed like this. From this mathematical expression of the wave, it said that what is the amplitude, wave number, wavelength, and so on. So first it says the amplitude. From this expression, it is y equals to the numbers or any expression before sine and cosine represents the amplitude. This is the amplitude, and it's 4 centimeter. Sine, then here you have x variable. In front of x variable, we have a wave number kx minus, since it is minus, it's moving to the right side, so you can have minus. Then here you have t variable. In front of t variable, you have omega plus, here you have a function wave shift. It's known to be wave shift. You can have such an expression. Previously, the general function of the wave is expressed like this. So from this, 4 centimeter represents the amplitude. Here we have x sine, here we have sine. In front of x, 0.5 pi represents the wave number or the propagation constant or the wave constant. So the propagation constant can be determined as what? K is equals to 0.5 pi. But K, we know that it is given to be 2 pi over lambda. It's possible to find the wavelengths. To find the wavelengths, you can use K is equals to 2 pi over lambda. Wave number equals to 2 pi over wavelengths. From this, wavelengths can be determined as 2 pi over, since we have already determined the propagation constant or wave constant, 0.5 pi rad per meter. You can put it here so that the wavelength is found to be 4 meter. And then it says angular velocity or angular frequency. Okay, angular frequency or angular velocity is represented as omega. In this case, variable in front of time is known to be angular frequency. So 10 pi rad per second gives us the angular frequency. And the linear frequency can be determined as, we know that omega is equals to 2 pi f. This is the angular frequency, whereas this one is the linear frequency. So to determine the linear frequency, it's possible to have f is equals to omega, the angular frequency, over 2 pi. Already you have found that 10 pi is the angular frequency. When you substitute here, you can find it to be 5 hertz or 5 per hertz. And it says the phase angle or phase shift is possible to have pi over 6 rad. By the way, all the units here must be in rad. The unit of K is rad per meter. X should be expressed in meter, so that when you eliminate, you can find it to be in rad. Omega is rad per second. Time t is second, so that you can eliminate. And at last, if there is a phase shift, pi should be expressed in rad, so that all the quantities here should be expressed in rad. So this is how we represent mathematically a wave, or wave is expressed using this way. Now let's try to see about the properties of waves. Waves have so many properties, but basically we have 4 main categories. Wave can reflect whenever there is a boundary. There is a reflection. There might be a refraction waves as it propagates from one medium to the other medium, or when there is a transmission, they might refract. There might be diffraction. Waves has a tendency to be scattered whenever there is a gap or there is an obstacle. Or it might interfere. Okay, waves can interfere. If you have two waves, one wave might be interfere with the other waves. So the four main properties of waves are reflection, refraction, diffraction, and interference. So reflection, here you have interference. So among the four properties, we mainly focus on reflection and interference. Reflection is a rebouncing of waves from a given boundary surface. The wave from a source is known to be incident wave, and the wave which is rebounced back from a given boundary is known to be reflected wave. So as these two waves merge together, they will form an interference pattern. So waves might be summed together or interfere together and forms a different pattern of the waves. So here, these two waves are known to be in phase, meaning the corresponding points are found at the same location at the same time. So when two in phase waves are summed together, there is a constructive interference. The result is going to be constructively interfere. But here the two waves are known to be antiphase, meaning their corresponding points are not located at the same time. Here the trough is found at this point, whereas for this wave is a crest is found, meaning the negative value and the positive value, when they are together, they are cancelling out together. So this wave is cancelled by this one is cancelled by this one, this is negative, this is positive, negative, so that all are going to be cancelled out. Such interference of waves is known to be destructive interference. Here they interfere constructively, but here they interfere destructively. So here it says at some angle you might have different interference. You can see this. Now among the interference effects of waves, here you have a so-called known to be standing wave. A standing wave is one of the waves which is a result of interference of two waves. And it's most commonly found in musical instruments. Every musical instrument, whether it's piano or it might be guitar or something, any other instruments, use a standing wave, which is a combination of incident wave and reflected wave merged together or interfere together, and they form a standing wave. So standing wave is a combination of two different waves. It's most commonly found in musical instruments. It might be string instruments like guitar, it might be car like us, and so on, or it might be air colon. Air colon means saxophone, or it might be flutes and so on. Okay, and the mathematical expression of a standing wave is expressed using 2a sine kx omega t, because that there is incident wave expressed to the right like this. You can have kx minus omega t. There is a wave which is propagating to the left. You can use plus. So the addition of these two gives us the equation of a standing wave. So standing wave can be expressed mathematically using 2a sine kx omega t. This wave is standing at one point, but it has a fluctuating amplitude, okay, at different time t. Whenever there is a different time t, there will be, you can find a different location. You can have up and down points. And these points are known to be points with maximum oscillation is known to be antinodes. Antinodes are known to be points with maximum oscillation. And there are points with no oscillation. These points are known to be nodes. We call it to be nodes. So these are the 2 points found in standing waves. And the distance between 2 successive nodes and antinodes can be mathematically expressed like this. For example, here you have a wave. This is one complete wave. This is known to be lambda, since it is one single wave. And therefore, the point here is known to be nodes, because no wave or no oscillation. The distance between 2 successive nodes, node here and here node, is lambda over 2. Whereas the distance between node point and antinode is known to be lambda over 4. Okay. Here lambda over 2 is the distance between 2 successive nodes, or antinodes is known to be lambda over 2, but the distance between node and antinodes is known to be, or having lambda over 4. Standing waves for embossed. For example, here you do have a string which is fixed embossed so that you can produce. The harmonic series, we have harmonic series or frequencies might be formed. This might be the fundamental frequency of a string fixed embossed, or you might have different harmonics, the second harmonic, the third harmonic, and so on. So the mathematical expression of the string which is fixed embossed, the nth harmonic can be determined as n times v over twice of the length L. This is how we express the frequency of the harmonics frequency of string device which is fixed embossed. For air column, we have two types of air column, which is both end open is known to be open pipe, and if one end is open, the other end is closed, is known to be closed pipe or known to be stopped pipe. So the mathematical expression for open pipe, which is open embossed, is the same as that of the string, which is n times v over 2L. This is the same expression as that of a string device. But for closed pipe, the nth harmonics can be determined as n times v over 4L. This is how we express for closed pipe, which is closed at one end and open at the other end. Okay, this is true for closed pipe or known to be stopped pipe. Nv over 4L, and note that n should be odd harmonics. There is the first harmonic, the third harmonic, the fifth harmonic, and so on. There is no even harmonics in closed pipe, and don't forget that. And at last, let's try to see about sound wave. We have different waves. Among that, one good wave is sound wave. Sound wave is a mechanical wave, and as well as it's a longitudinal wave. It's longitudinal because that the disturbed particle has the same orientation as that of the wave. As the wave propagates in one direction, the disturbed particles are moving along that wave. So that it's longitudinal wave. Sound wave is a longitudinal mechanical wave. Depending on the human hearing ability, it's possible to classify sound into three, as audible sound, infrasonic, and ultrasonic sound waves. And the frequency varies 20,000 hertz. The audible sound is from 20 hertz to 20,000 hertz. Whereas the infrasonic has a frequency which is less than 20 hertz. Ultrasonic sound has a frequency which is more than 20,000 hertz. This is what it says. And the velocity of sound wave generally can be determined as the elastic property over inertial property. Previously, you have found wave for a tension string as root of T over mu. Okay. Among the elastic properties are modulus. Modulus are elastic properties. Inertial properties are known to be density. For example, the speed of a wave for solid bodies generally can be determined as Young's modulus over density. This equation is derived from this one. You can find it on some books. And the velocity of sound in liquids is generally given as bulk modulus over density. But the main case is how do we determine the velocity or the speed of a sound in air. Okay, the speed of sound in air can be determined as 3031 meters per second. This one is actually the speed of sound at 0 degrees Celsius. Speed of sound, V naught, you can say that, it is 331 meters per second at 0 degrees Celsius. And for every temperature rise, there is 0.6 meters per second increment. So that it's possible to have 331 root of 1 plus Tc over 273, or easily it's possible to have 0.6 times temperature expressed in degree Celsius. For example, here, what is the temperature at 10 degrees Celsius? If it is 10 degrees Celsius, 10 degrees Celsius times 0.6 gives us 6. So 6 times 331 gives us 337. So at 10 degrees Celsius, the speed of sound in air is 337 meter per second. So depending on temperature, its speed varies. And the other thing is sound loudness and intensity. For a given sound, its loudness might be expressed in terms of intensity. Intensity can be mathematically expressed as power P over area. And area can be measured as, for example, here we have a source. And as sound is propagated, it's propagated in all directions. Suppose if I am a source, the sound is moving here, upward, downward, in all directions, forming a spherical wave pattern. So here we have a source and there is a spherical wave pattern. At a distance of r from this, we have a spherical wave pattern, and that spherical wave pattern has a surface area. And that surface area is given to be pi r squared. We can have pi r squared. So intensity I is equals to P over area. If you have a constant power, the area might be changed at different location. Here, at this location, the surface area is this one. At this location, we have another surface area. So that it depends with r, with the radius r. So when you put it here, you can find that intensity I is equals to power P, for a constant power P, 4 pi r squared. Now look here, the intensity varies for a constant power P. The intensity is inversely related with the square of the separation distance from a source. So intensity I has inverse relation with the square of the separation distance r squared. This is one of the cases. And the other case is intensity might be related with that of the amplitude of a source. Keeping the distance constant, it's possible to have intensity as 1 over 2 density rho. You can have the speed of a wave, omega squared, amplitude squared, and so on. These are the constant variables. The only thing which varies is the amplitude. For example, if I am talking with higher amplitude, if I increase my amplitude, the intensity reached there is increasing. Whereas if I decrease my amplitude, the intensity is decreasing. So that intensity has a direct proportionality with the square of the amplitude, and it has inverse relation with that of the square of the separation distance. And the other thing is the unit of sound intensity is watt per meter squared. Is somehow a very larger unit. We have equivalent expression of sound wave, and it's known to be decibel, logarithm. And intensity in decibel can be given as 10 times the logarithm I over I naught to the base 10, where I naught is the minimum sound intensity which can be detected by human ear, and it's known to be threshold of hearing. And it is 10 to the power of minus 12 watt per meter squared. So it's possible to convert any given intensity in watt per meter squared into its level or equivalent representation, or if it is given in sound level like 80 decibel, 40 decibel, you can convert it into watt per meter squared. Okay, keep this in your mind. Here you do have hearing curve. It's a curve used to correlate the frequency, the intensity, and so on, as well as the pressure of hearing ability. For human being, it varies from 20 hertz to that of 20,000 hertz. It's possible to have the frequency this way, the intensity on this direction. Hearing curve, this is what we call hearing curve. The range of hearing varies from 0 decibel to 130 decibel. Then the threshold of hearing, the actual threshold of hearing of human ear is 2.5 times 10 to the power of minus 12 watt per meter squared. This graph has, in your textbook, you can see that every number are there, so that it's 2.5 times 10 to the power of minus 12. This is actual hearing of human ear. So this is what you call hearing curve. At last, let's try to discuss about Doppler's effect. Doppler effect is one of the most applicable science, and it tells us how does a given frequency changes due to the relative movement or due to the relative position of the source and the observer or the listener. This is what we call the apparent change of frequency due to the movement of the source and the listener. There are different cases. Actually, it was derived or found by Austrian physicist Christian Doppler. That's why it says Doppler's effect. We have different equations. The main equation for Doppler effect can be given as a frequency reached at the listener is equals to the frequency of a source times the velocity of a sound in air minus or plus the velocity of the listener over v plus or minus the velocity of the source. You can classify this into two as approaching case and receding case. Okay, that means if the two objects, meaning the source and the listener, might be approaching towards each other, or the source might be stationary, the listener might tend to move towards stationary source, or the listener is there, but the source might be approaching. This all is known to be approaching. They might move together, or one is moving towards the other, so that's known to be approaching case. The other is receding case. Both might be moving oppositely, or one object stands there and the listener might move. So that we have different case, approaching and receding case. And the applications of Doppler's effect is most applicable. You can find it in military science, in astrophysics. You can find it in that of medication for measuring blood pressure. It's possible to apply it in transportation science for radar, controlling the speed of cars. It's possible to have apply it in different fields. As well as for engineering, it's possible to measure speed of fluids. Okay, so that's the most applicable field of science. So this is all that I've got for today. Next time we'll try to see about wave optics. So this is all that I've got. Bye bye.